We're looking now at linear operators and trying to understand how an operator can be used to analyze a function and thereby understand that function's behavior. A linear operator is a special case of an operator, which we look at in detail just now. Here's an example of a linear operator. So an operator in general will accept a function as its argument, and here we have this linear operator which we've defined. So we are calling this operator alpha, and alpha is accepting this function f as its argument, and this linear operator multiplies f by a constant a and adds another constant b to it. And so a and b are just scalar constants, and the result of this operation is to give us back another function. So we may think of operators as functions that operate on other functions and give us back functions. So in this case, if we use, for example, the function sine of x, then if we apply that in here, then the result of this is going to be the function a sine of x plus b. So that's pretty straightforward. That's quite clearly a linear operator. And some of the properties of linear operators, and in fact the name almost automatically implies these types of properties. Additivity, so if we perform an operation on the sum of two functions, then we get the same function if we perform the operation on the individual functions and add those together. So that's additivity, much expected. And then homogeneity of a scalar operation. That's if we have some scalar multiplied to the function and then transformed, then operated on, we get the same result if we perform the operation on the function and afterwards multiply by the scalar. So that's another one that's pretty well expected in linear type operations. And the third one is really a consequence of these two. So if we have a scalar multiplied with a set of functions which is all being added together, if we do an operation on that, then we can get the same result if instead we multiply the scalar separately to the operation and we perform the operations on the functions independently and multiply and add all those together. So that's associativity of the addition operation. So in this example, we used something that's very clearly a linear operator. Now let's go on to using integral functions as our operators. So in this case, we continue defining alpha to be our operator, and I'm not saying it's linear as yet. So in this case, the operation on f is that we are going to multiply f by this new function g of s, and we are going to integrate the result of that multiplication from minus infinity to infinity. So we are integrating this new kernel of f times g. And in this example, we are using g as being a function which is 1 in the range x between, x from 0 to 1. And if it's not from 0 to 1, then it's a 0. So this is in effect a filtering function. It's going to admit any values that are between 0 and 1, and it won't admit a value. It will zero out a value if it's not between 0 and 1. So in this case, if we go and multiply g of s by f of x, and by the way, there is no s dependence, right? In this case, this is a trivial function in s because s actually doesn't appear here. In fact, g is more a function of x in this case. So anyway, we multiply g of s by f of x, and then we can see that the only time that f will survive, so the only time it's, this product is non-zero, is when g is when x is between 0 and 1. So instead of multiplying all the way from minus infinity to infinity, we can say it's only non-zero between 0 and 1, so we may as well just integrate there. And then we know in this range that g is going to be a 1. So we can simplify this whole expression. We reduce the limits of integration to between 0 and 1, and we then just specify f of x. G is a kind of silent 1 in here. So that's alpha, and if we think about this function, this is in effect an averaging procedure, right? If we want to integrate, if we want to find the average of a function between two limits, then we would integrate that function between those limits and then divide by the range in those values. So if this was between, for instance, 0 and 5, then we would integrate this from 0 to 5 and divide by 5. Anyway, this is from 0 to 1, so this is in effect the average value of f between 0 and 1. So that's an example of an operator. So in this case, we are getting back the value of the function, the average value of the function between certain limits. So this is intended to show us that an operator can be used to extract some specific information about a function. So if it so happened that all we wanted to know about this function was what its mean value was in those ranges, then we could use this linear operator to find that out. Alternatively, if we did want some kind of if we did want to know the average value in a particular range, let's say instead of between 0 and 1, we wanted to know what the mean value of the function was between s and s plus 1, then we would redesign this function g of s. So we can design this function so that we can extract the features that we want for f. In other words, we are redesigning our operator such that it yields the specific information that we want about this function f. So in this case, we want to know what the mean value of f is between s and s plus 1. So this time we define g of s to be 1 only between or from s to s plus 1, and we zero it out everywhere else. So now our integral simplifies to between s and s plus 1. And actually here, I'm just switching back to the code view. This should say s to s plus 1, right? S and s plus 1. And the reason that was different is because we look at some code just now, and in that code, it's actually, I've done things a little differently there, but we'll see that just now. So anyway, that's how we can extract the mean value of f between a slightly more specific range. And in this case now, g is a function of s. It is also a function of x, but it's now you can see the influence of s. So if we want to be a little more specific about the information that we want about f, we can do that through the parameter s in this case. And in this example here, I'm just, this is all a Jupyter notebook, so we're looking at Python code here. So I'm importing some functions from a bunch of libraries. You can see NumPy and SciPy, the usual libraries for mathematical operations, some plotting libraries, and then some interactions, which we'll use just now. So anyway, we want to now view this. We want to try and understand what this kind of example gives us in the result. And here we are specifying an x range between -5 and 5 using 3,000 points. So this is a linearly spaced set of points from -5 to 5. Let's just set this down to 1. I'll explain what ds is just now. And in this case, I'm using f of x as sine of x, noting here that we have to use the NumPy library to use the sine function. So the sine function is actually not available by default in the root of Python. So that's f of x equals sine of x. And then we are also defining here a function g of s. And in this case, I want g to be 1 between s and s plus 1. So I'm just going to comment, I'm just going to comment this line out. And let's create a function that returns a 1 between 0 and 1. So let's create a condition. We can say if x is more than or equal to 0, and if it's less than or equal to 1, right? That's our condition. Now, this is a condition, and that's going to return for us true and false. So if we stick in a bunch of x values, we'll get false if we are not in that range, and we'll get true if it is in that range. But we don't want false and true, we want 1 and 0. So we want to convert this Boolean number into an integer. So if we say, instead of accepting a Boolean output, if we say as type int, then that's going to coerce this Boolean variable into an integer. And of course, we know that true values of true we can represent with a 1, and values of false we can represent with a 0. So here we'll get a true if we are in the right range, and then when it's coerced into an integer, that becomes a 1. So we get a 1 as we want in that range, and we'll get a 0 otherwise, because then this will be false, and then that becomes a 0. Right, so that's how we can define a function g in this way. Right, so our function g is defined there, and then down here we can see we are preparing another function. So in this function, it's first going to determine the values for f using x. So using sign of x, we are going to get a set of numbers here, which we'll store as y. And similarly, we will store a set of numbers for z using g. So y and z are basically f and g. And then we can just multiply those two together, and then we can integrate that. Right? So we are in effect writing the function which is going to do this for us. We generate the set of f values, we generate the set of g values, multiply them together, and then we integrate. And of course, this is the symbolic form. If we are doing it numerically, we've got arrays of numbers for these two. And so we need to use something like trapezoidal integration for those numbers. And so we are using here the cumulative trapezoidal rule. So if you look up here in the libraries, we have imported the integrate method from SciPy. And in that integrate class, I should say, there is a method cumulative trapezoidal. So that's going to integrate our product. Now remember, a is the product of y and z, so it will integrate a with respect to x and use an initial value of that integral of 0. And what this part will do is return for us a vector of numbers at each value of x. It's going to tell us the cumulative integral up to that value of x. We don't want all that. We just want to know what's the final integral if you integrate in that range. So if we just specify here, just give me the last value. That's how you specify the last value of an array in this language anyway. So we just pull out the last value, which is going to be the integral over that range of x values. Then that's going to be the integral that we want. In this case, I happen to be dividing by ds. That's a 1. We'll come back to that. So for now, it's dividing by 1. It doesn't really make a difference to us, right? So this then is exactly what we have formulated here. We want to know the integral, and we've generated all the numbers we need to do that. And we can go ahead and plot all this. So we can plot x against f and x against g, so we can see what those look like. Then we can look at the kernel as well. So f times g, we can plot that. And then we are also plotting this value, right? Remember, this is a single number. It's the integral over that range. We've integrated out that variable x. So this is not really a function of x anymore. But anyway, we are just putting this so that we can see it next to those other functions. And here, this little string tells us, since this is a single number, just put it down as a single dot. Right, so that's the plot, and then we want to control our limits on the plot as well. So we create a handle to the axes of that plot by this statement. So we write in plot dot get current axes, right, GCA, and then that returns for us a handle axes, and then we can set the y limits and the x limits, and we can label the axes and all of that. So that's the function which is going to give us the integral and plot it for us. And we also want to create some interaction. We want to be able to change the value of s so we can see how this function changes or how the result changes. So we say here interact, and we create this variable s, and by writing it this way, remember int g is the name of the function that that does all this work for us. So we pass the name of that function here, and we specify an initial value for s here, and then that's going to give us this little slider down here. So let's run this block. Oops. So here I think we need just one ampersand for the and in this language, right? So that's run, and now we can see here f of x, we specified that to be sine of x, so you can see that sine wave here. We specify g of x to be 1 between 0 and 1, and you can see that here, and then it's 0 everywhere else. So that's our function g. Then a is the product of f and g. So because g is 0 here, then the product of those two is also going to be a 0. So as I say, we have also calculated the integral under this curve a. So the integral is shown here as this red dot. So let's just drag back this s value, and you see here that function g is not changing as I change s. And that's because I've set very fixed limits here for g. So let's change these. So we want to change this to be 1 between s and s plus 1. Right, so now you can see that's coded into this function g. Now it is a function in s, and let's rerun this. And now as we drag it, you can see the function g depends on s. So when s is this value, then g is non-zero only between this value and 1 plus this value, and then we can see the mean value is changing. Right, this integral is now in this range, and in fact, it's a little better to show where that sits in between these numbers. So let's, instead of plotting that there, let's plot that at the point s plus 0.5. So remember, here we are plotting a single point. Here these are all vectors of numbers. Here we are plotting a vector, an arbitrary vector of length 1. So it has just the element for the x value of s plus 0.5 and of the final integral value of IA. Let's rerun that, and you can see now that mean value, or that integrated value, is sitting quite close to the function f. So we could, of course, change that, change the width of this. So instead of integrating from 0 to 1, we can change that. Let's say ds is something like a 3. So we would have here s to s plus ds. And now, of course, the interval is different to 1. So if we really want the mean value, then we need to divide our integral, which is now going from s to s plus 3. We need to divide that integral by the range there, which is 3. And that's already done here. That's why we had that ds factor in. So let's rerun that. Remember, Control Enter is the shortcut in Jupyter Notebook. So now you've got this bigger range, and the dot's a little bit in the wrong place, because instead of 0.5, we should do this at ds plus ds over 2. All right. Okay. So we can see now that over this bigger range, the dot doesn't track the function f so closely anymore. So if we look in this range, if we consider all these y values, this is a better indicator of the average over that extended range. Right, so that's how we can numerically estimate these values. So, of course, in our transformations, we do get functions out. We can get analytical forms of these functions, but we can also get numerical estimates of the functions as well. So all of these operations are not mysterious or complex in any way. Well, they actually are complex, but in the strict sense of complex numbers, but they're not complicated and not mysterious. We can operate on these using the usual calculus operations that we are familiar with, and we can also do numerical operations on these. So that's all operating like we expect. Now, we can think about this, and this is giving us some local information about the function. So this specific operation gives us the mean value in a specific region of the function. But more typically, operators are used to find information about the whole function. So usually you try to extract features about what's the important frequency for a function, or which regions do the functions go into. So that is a kind of more general application of operators, and we'll see that in this example. So in this case, instead of using g of s in this discontinuous specific range, we are now looking at g of s as being a sine wave function itself, and so our operator looks like this, and here we are just writing in g of s, and g is sine of s times x. So of course x, that's our independent variable. It's in the domain of f, but now we are introducing this s, which is going to scale our x. So for higher values of s, we are going to get a higher frequency of our sine of x, and for lower it will be lower, and so on. So let's look at how that will respond now. So we use a very similar set of code. We're using x in the same range. This time we are setting a range for s, so s between 0 and 3, using a resolution of 200. Here we are using the same f function as before. For g, we are using sine of s times x, as we said. So the same function as before as well. We evaluate y and z, and then the product of those two, and then we integrate over all x values, and then we plot that out. So this is exactly the same as before. All right, so we interact them like this. And I'm just going to comment out this part, which we'll look at in a little bit. So let's run this. And I'm just going to set s down to a low value first of all. Right, so we've got our function f of x as we are used to, and for g of s we have a flat line here, and that's because we've set s equals 0 at this stage. So when s equals 0, then it's sine of 0 everywhere, no matter what the x value is, so that's a flat line. And now as we start increasing this value of s, you can see that g starts to become more non-zero. Of course, it will still have zeros at certain x values, but it's a very low value, so we've got these numbers in this range. And as we increase that, you can see our g function, we can see more of that sine wave, right? Remember, we've restricted the range here, but so as we increase that, you can see our g function, and we can keep increasing the value of s, and we get a higher and higher frequency for g. Right, so g is oscillating quite rapidly, and we can see in the background our f function is still there. And if we think about this, well, we don't have to think about it. We can see it here. We can see the product of f times g, right? This green line is that product that's plotted out there. Now, this product we can see is dodging rapidly between 0 and from negative to positive, right? It's oscillating between -1 and 1. So if it's doing that in a symmetrical way, right, if we have equal amounts of positive and negative values, then of course that's going to get close to 0. Right, so the integral under the curve for a, given that 0 is cutting through here, the integral under a we anticipate will be some number close to 0. Right, so that's what happens when we use a high frequency for s. When we use a high value for s, we are going to get lots of oscillation, and it's a symmetrical oscillation because it's a sine wave that we used, and so we are going to get zeros here. If we drop this back down again, right, at 0, at s equals 0, g is now 0 everywhere, so of course trivially that's going to be 0. But even at lowish values for s, right, if s is 0.2 for instance, then you've got a number which is going from a negative value to a positive value in a symmetrical way again, and we anticipate that if you extend the range that you are going to get equal proportions of positive and negative values. So when you integrate under that curve, you will still get a number close to 0, right? The positives and negatives in effect cancel each other out. So the product function you can see here is more complicated now, but it's in fact, let's extend the range a bit to see that a bit more clearly. So instead of -5 to 5, we go -50 to 50, and let's increase the resolution as well. And you can see that here the green function is it's got that bit of a blip here, but it's quite it's oscillating quite rapidly, and so the number is going to be small. It's possibly not 0 because we can see this concentration in this range here of some positive values, so perhaps the mean is not 0 anymore, but well, in fact I'm looking at the wrong frequency, so let's put it back here. We had 0.1 before, so yeah, you can see that. So you've got at low frequencies in S, you get this positive and negative sort of balancing each other out. Now let's see what happens as this number increases. So we've talked about at low values of s and at high values for s. Now let's take that up to a 1. So now in this special case, we have s equals 1, and if you think about our function, when s equals 1, that means f and g will be equal. So this is the case where we have the two functions equal, and that means no matter what the sign is, those two functions are going to yield a positive or 0 value. So if f and g are positive, then the product is positive. If f and g are both negative, then the product is going to be positive. So in this case, we have a kind of reinforcement effect. And so at a value of s equals 1, we expect to get the largest value for our function, for our transformation, right, for alpha. So once more, at low values for s, we expect to get low values for our transformation. At high values of s, we expect also low values for our function, but at values close to 1, where the two frequencies line up, we get some number that's not close to 1, right? And we can see that more clearly if we plot out, instead of looking at individual values for s, we could generate the whole function. So here's another function definition, and here I'm running across all those values for s that were defined here. Remember, I defined s from 0 to 3 using a resolution of 200, and here we can see we are generating, well, we didn't need to regenerate the values for y here, those don't change with s, but anyway, we regenerate z, and then we integrate that and we get a new value for that integral, and we store that in this this vector I. And then out here we plot the vector that comes out. So we set is to be the result, which is a vector, and we plot s against is. And if we run this, we can see here that you've got the spike near 1, right? And it's much more than 1. And you've got these lower values here. So as we said, for lower values of s, you get low integral values. For higher values of s, you get low values. Only near 1 do you get the spike. And in fact, these are just artifacts of the integration. Because we've cut off the integration at these low ranges, we get this. If we increase the range further, let's take 500, and I'm not sure that's going to work. That might be a bit high for the memory. Yeah. So anyway, you can see as you increase the resolution and the range of your integration, you are getting closer to a spike here, and you're getting closer to 0 everywhere except at that value of 1. So I've been pretty verbose about the details of what we are doing, but let's take a step back and think about that. That's telling us that in our integration, right, when we do this operation, we have found a feature of this function that's telling us that this number of 1 is significant. Right? If we look at the result here, there's a single value where we get this sharp value that's far from 0. So it's telling us this value of 1 is important to us. So that's in effect telling us the frequency at which our function f is, it's telling us the relevant frequency for this function f. And we acknowledge that we chose to look for frequency by doing this, right? By setting g of s to be sine of sx, by letting s be in this position, which is acting like a frequency, we are then creating an operator which looks for frequencies in our function f of x. And we got a result which is kind of obvious, right? We know that f of x has a frequency of 1. So if you go and do this operation, of course, it's going to tell you at 1 there's something important going on, right? So our definition of f, which is sine of x, where did we... Right, so up here we said f is sine of x, so there's a hidden, a kind of silent 1 here. So there's clearly the frequency of 1 was always going to appear. But this is because we set that value. Now, we don't always get to set this value of x, right? F may possibly be available to us only as a set of values from an experiment, or it might even be plant data. So perhaps we were measuring the temperature on some unit on a chemical process. So we don't always know f of x. We don't get to choose our frequency. We don't know what the frequency is. So this function f is describing some underlying process. And of course, we want to control that process. We want to design some control strategy around that process. But we don't know anything about the behavior of that process. But now we have a way to extract information about that process. We can go ahead and create a function.
Daddy, listen to me.
Yes, Carol.
Please, can you put on again for me?
Right. So f might be some set of values, and we can just stick those numbers in here. And similarly, we can generate the set of g values by using this function. So this function we have to create. F of x doesn't have to be generated from a function. That can be a measured set of numbers. And then we can generate values for g at those values of x. And then we can numerically integrate that, and that will tell us alpha of s. And then we can go ahead and look at the result we get, and we can say, yes, there seem to be frequencies in these regions, and so that's how we can extract information about a function. And by the way, you might recognize this as the Fourier series. So that's a special selection that actually has many other implications. And sorry, the Fourier operator. So that's a famous operator that's used, or a famous kernel that's part of the operator, right? You have to integrate it also. So that's a famous operator here. And that's often used in frequency analysis. So that's those are examples of operators, and that last one is still a linear operator, and you can test that using the properties that were defined earlier. So we had defined these properties for our linear operators, and you can test, you can try different functions for f and g, and see that that operation satisfies those properties. So now in what we'll go on to next is the so-called Laplace transformation. So it's defined like this. We use the special symbol for this operator, and it really is a special operator. It's quite phenomenal, the things we can do with this Laplace operator. So it's defined in this way, and it looks deceptively easy. We've got a function, we've got the exponential function, so e to the minus st. So s is in this position. It occurs as a coefficient of the time. So time is the independent variable. So the original function that is in time now, not in some arbitrary x like we've been talking about. So that's in time. And the Laplace transformation does also use time in its argument, and its main parameter is s. And that's the exponential, and we are integrating from 0 to infinity, so it's defined like that, right? Of course, in an operator we are free to pick those integration limits as well. So this specific operation gives us new insights into the function f, and surprisingly many insights. In fact, it gives us a completely new perspective on f that lets us do crazy things. We can do integration. We can find integrations of differential. We can find solutions to differential equations that are in fact not possible without the Laplace transformation. Now we can start to understand why this is so significant when we accept that s can be a complex number. So if s is complex, so it has real and imaginary parts, then when we expand out s to a complex number times t, then it looks like this, right? You've got e to the, this is the real part, so sigma t, and then cos of omega t plus I imaginary sine of omega t. So that's the real and that's the imaginary part. And you can see here we've got cos and sine, so we'll see that this is in fact a special, this is a more general form of the Fourier series. And we also have an exponential part. And that exponential allows us to capture that sometimes the function is dying out in certain regions and so on. So that's why this Laplace transformation can be so effective, right? It helps us capture frequencies. It can also help us capture regions where the function is dying out or leading up and things like that. So the Laplace transformation is something that we'll spend some time getting used to, playing around with what's possible through it, and that will be the basis of our frequency domain dynamics.